Okay. So section 3.1 in the new books, that's page 246. I suspect that's 20 pages off somewhere or another, Sam. I bet you can find it. Okay, this is the last chapter we're doing in this course. Exponential, logistic, and logarithmic. Do not get those two confused. They both start with LOG, but they are way different from each other. And today we're going to introduce you to exponential and logistic, not logarithms yet. No logarithms yet. These are both based on exponential things that happen. Okay. Just briefly, I always like the chapter overview, kind of give you a sense of where we've been and where we're headed. So I'm going to read that here. In this chapter, we study three interrelated families of functions: the exponential, the logistic, and the logarithmic. Sound like way different. Polynomial functions, rational functions, and power functions, which we just finished studying, they are, and also things that have rational exponents, they're all algebraic functions. That's what we call them. They're classed by themselves, algebraic functions, because they are obtained by adding, subtracting, multiplying, and dividing constants and independent variables. X. All the different ways we can put X in different places and study different attributes for it. In this chapter, we begin to explore transcendental. Transcendental means to go beyond or to transcend the algebraic operations. There's going to be a lot of skills and a lot of things that you learn about these guys where the algebra that you know will not suffice. You'll have to know other rules. You'll have to know other strategies for getting equations solved, for example. Happily, this is stuff you've seen before. You should have seen this in Math 3. Did you? Exponents and logs? I'll help jar your memories loose. But anyway, just like their algebraic cousins, exponential, log, and logarithmic functions have wide applications. Exponential functions model growth and decay over time, such as unrestricted population growth and the decay of radioactive substances, for example. It also has to do with the diminishing pressure in the atmosphere as you go up. That's exponential and logarithmic, I guess it's logarithmic. Things like that. Logistic functions model restricted population growth. That means over a long period of time where, we'll talk about that. We'll talk about the Great Bunny Bash of 1984. You talked about that before? All right, okay. Certain chemical reactions get buffered. You know what a buffer is in chemistry? Slows it down. You got a catalyst which speeds it up. You know those things? And so you can speed up the growth, and then you can add a buffer and slow it back down. Most common buffer that I'm aware of is antifreeze. Doesn't allow temperature to change too much in the extremes, which is helpful in cars. Anyway, that's neither here nor there. Logarithmic functions are the basis of the Richter scale for earthquakes, the pH acidity scale in chemistry, and the decibel measurement when you're talking about sound. We'll talk about all of those as we go through. The chapter closes with the study of mathematics of finance, which is an application of exponential and logarithmic functions used when making money choices. We may or may not do that section. Depends on if we have time. We've already lost a day that I planned on not losing, so we may not have to do that section. And if that's the case, then at least 2 of the 3 questions on the test pertaining to that will be bonuses. But we will have to do a little tiny bit of the finance section because it's required at ISU. Anyway, moving on. Here we go. 3.1 is called exponential and logistic. We're going to focus on exponential for a while, and then we'll switch over to logistic. I'll let you know when that happens if you're not paying attention. In your calculators and in all books I've ever seen, the exponential function in a general way, like we talk about parent functions when we do things, exponential function is y equals ab to the x. There's 4 things here. Does it make sense to you, just looking at that if x is allowed to be 0, then y equals a? Okay, I'm going to change one of the variables. I'm going to make this t because these things are practically always, not every single time, but almost always, a growth with respect to time. As time moves along, something's growing. Either your money's growing or the population's growing, or maybe those are decaying. You're losing, if your stocks and bonds are not as lucrative as you thought they were, and they're losing value. But this is usually a function, this over here is a function of time. And it's usually the value of something or the size of something as a function of time. So now let me ask you that question again. If we start the stopwatch right now, that means time is 0. The value is A. That would be the initial value. That's what we call it. The initial value is A. Because if time is 0 and we're starting the clock right at this instant, then this is B to the 0. And you end up with the value of the substance or the population or your money is this. This is your beginning value because that's what happens when T is 0. So this is the beginning amount. This right here is, like I said, almost always time, but not all the time. Almost always time. We're going to see one example that has to do with the atmosphere, like I said, later on. But it's usually always time. That's your independent variable. Because you can't control time, it just moves on ahead no matter what's going on. So that's your independent variable. This is your dependent variable, and that is the value, whatever we're studying, it's the value after T units of time. And it's constantly changing because time is constantly moving ahead. If we're talking about, you know, the dynamics of one of these things. And this guy right here, probably the most important thing in this that makes it exponential. It's always a constant, folks. This is always a constant. And it's always greater than 0. B must be greater than 0. And it is we call it the base. But what that means is that that number right there is the number we're going to use over and over and over and over and over again as a multiplier this many times. That's what that means. B to the 4th would mean to multiply by B times B times B times B. Okay? So this is your multiplier over and over and over again. This is where we start. It was only used once, but this is used this many times as a multiplier. And as you do that, if this is, here's the deal about B. If B is greater than 1, well, I'm going to go ahead and say this. If B is greater than 1, then you have a growth. So long as T is positive. You're going, how could T ever be negative? They can't if this is time. But when we're studying exponents as a concept, this could be negative. Well, you'll see it in just a minute. I promise it'll come together. And if B is trapped between 0 and 1, in other words, a proper fraction, then whatever's happening is decaying in value. A good example of that for money is, for example, if you are going to invest money, just say in a bank that's paying 5%, then B is 1 to hold on your investment, 0.05 to add 5% to it. And 1.05 is greater than 1, so your money is growing. Not very fast initially, but it's growing. Or you might have a decay in the same situation. If you go and buy a car, as soon as you drive it off the lot, it's worth less than it was when you just bought it. Because as soon as you buy a car, time starts, and cars, what's the word? They decay in value. And so like if you have a decay rate of 14%, then B will be 0.86. Because 14% is 0.14. This would be 0.86, which is in here, means your value of your car is decaying. So that's just a couple of examples of where we would see this. Now, let's take a look at some instances of this and see if we can recognize in the formulas the things that they want to ask us. First of all, in example 1, they want to see if you can recognize an exponential function when you see it. So in part A, please don't look at the solutions. Well, they explain it right afterwards. But what I want to know is f of x equals 3 to x. Do you believe that's an exponential function? Yeah. All right. If so, what is A? 1. What is B? Growth or decay? Don't say growth or decay yet until you figure out the value of x. If x is positive, it's a growth, right? Yeah? Okay. Next one. Is that an exponential function?
No, because x isn't this.
No, because You got the first part of it right. No, because x is not a constant. That has to be a constant number. They flip these two around. They put your variable down here and your constant up here. When you do that, you got a polynomial. This one isn't a polynomial because -4 doesn't make it a polynomial, but we call that thing a power function. You remember studying those? Power functions? That's a power function. That's not an exponential, okay? C part. Does that look like an exponential function? It does. It may not make a lot of sense based on what I just told you, but we can identify the pieces of it and it seems to match. What's A? -2. What's B? Row 30K. Well, with that negative, it's hard to tell. Could bring things down. Well, that's neither here nor there right now. Look at the C part. Oh, we did that. Look at the D part up at the top of the next page. Exponential? Actually, it is because we made no stipulation as to what x had to be, and x can be negative. But you need to understand this before you identify A, B, and C. If you have 2 to the negative x, that's the same thing as 1 over 2 to the positive x. Do you agree? Which is the same thing. Let's see if you buy this. Which is the same thing as 1/2 to the x. How can we do that? Well, 1 raised to anything is still 1. 2 raised to the x, and so I could say that this, that this was raised to the x, and that means I can pull that x that was applied to both of those back out front here. Back on top here. Because if you simplified this by working the x in, you'd get 1 to the x over 2 to the x. But anything, 1 to the anything is just 1, so these are equivalent. So you have to be careful when you identify A, B, and C on this. We agreed that it's exponential, and A is what? 7, but B is 1/2. Okay, how about E? Does that look exponential? What's the problem there? Yeah, there's no variable in it. It's just Q of x equals whatever 5 times 6 to the pi is. And that's just a constant. It's just a horizontal line, not exponential. Okay, y'all recognize them when you see them, I hope? Now look at example 2. If we have the function just plain old 2 to the x, if we replace x with 4, in other words, if we do f of 4, we get 2 to the 4th, which we all know, I hope by now, is 16. If we do f of 0, that means 2 to the 0, and we need to accept that anything to the 0 is 1. Do you accept that, or would you like me to show you why? Anybody need me to show you why? You're good with it? Yep. Okay, two different arguments I could make for that. Okay, anything to the 0 is 1, so f of 0 is 1. F of -3 would be to take 2 to the -3, which is really 1 over 2 to the 3rd, and 2 to the 3rd is 8. So you get fraction them. Right? Y'all understand that? Yep. Next one, f of 1/2 means 2 to the 1/2, and we all know that that means the square root of 2. And it's irrational, approximately equal to 1.41. Am I losing anyone yet? I'm just stating what's in here. If we do f of -3/2, that means to let x be -3/2. That shoves the whole thing downstairs, and 2 to the 3/2 is, I hope you remember that, it's the square root, that's what the denominator is, it's the square root, and the 3 is the exponent. So you've got the square root of 2 to the 3rd, and if you make a decimal out of that, it's 0.35355. You're right. You understand all that manipulation algebraically? And you're going, I thought these were algebra functions. We're using algebra. Yes, you are. Just don't forget your algebra skills. These are still not algebraic. They're transcendental. We're just using some algebra skills to evaluate something. Okay? All right. He makes a big old argument and things about this, about raising something to the pi. It's very theoretical and tough to get, and it's not necessary. So we're doing it. In the next example, and I'm sorry, I wish that they hadn't put the things in here so that we could study it ourselves, but it's pretty clear here, and it'll show you what to do when you run into this. Remember the title of your book? Graphical, Numerical, and Algebraic? Well, here is a couple of exponential functions offered to you by the number, meaning numerical. It's a table. And you have to observe some things in order to write the algebraic equivalent of it. So notice that in both cases, we have two functions. We have g of x, which is in the middle. We have h of x, which is on the right. And we have x over there on the left. And so what they're saying is that the x's on the left belong to both functions, and they're different ones. They're different functions. So what we notice is that when x is -2, g has a y value of 4/9. And when x is -1, it jumps up to 4/3. So you may ask yourself, how do I get from 4/9 to 4/3? Because I'm going up the number line with the x's. How do I get from 4/9 to 4/3? And you can see it there in the green, or whatever it is in your book, Sam. You multiply by 3. And sure enough, 4/9 times 3 is 4/3. That's a little bit harder to tell the fractions. It's easier as you get bigger over there. When you jump from -1 to 0, multiplying 4/3 by 3 gives you 4. When you jump from 0 to 1, multiplying by 3 gives you 12, and the next one multiplying by 3 gives you 36. So it starts to get out of control there. You know, it's getting big fast. So what that means, folks, is, remember I told you B was the thing you use over and over and over and over again to multiply? Okay, so B, in this case, is 3. So numerically speaking, you gotta figure out, what do I multiply again and again and again to get the next successive term? That's B. What is A? Do you know what A is from looking at this, without looking at the solution? Nope. It's 4. Remember I told you that A would be the value that kicks out when the independent variable is 0? So look where x is 0. X is your independent variable. When x is 0, the y value is 4. So A is 4, B is 3, and so we would write that one, y equals 4 times 3 to the x. You have to be able to identify A and B from the numbers. B is the multiplier, and A is what happens when x is 0. Okay? So look at the next one. You go from one, as x goes up the number line, y seems to be coming down in value. So we go 128 divided, or time, well, you could think divided at first. 128, if you think about that, divided by 4 is going to be 32. Or if you don't think about it, you could divide 128 by 32 and get the 4. But then you got to convert it to a fraction, because you have to multiply by successive things. And the values here are decaying, so the multiplyer's got to be a fraction. In this case, it's 1/4. Does that make sense?
Yeah.
Okay, so your B is 1/4. What is A?
8.
8 this time. Y'all see it?
Yep.
Okay, so to write that equation, that was the A part, here's the B part. Oh no, that was, sorry, this should have been written f of x. Is that what they called them, F and G?
Yes.
Or G
Well, this
and
is
H?
H.
G and H? Sorry, that one's G. H is what we're writing here. That's the y value. Is equal to the beginning amount we said was what?
8.
8, and the multiplier?
1/4.
1/4 to the x. That is that function which will generate those values when x is whole numbers, well, integers. So you see how you get numerical values to translate to this? What you gotta look for? Good. All right. Moving on. I want you to look clear over the bottom of, it's 249, but it's the next page, Sam. It says it's an exploration, I think. Just below the exploration, there's a summary there. Can you see it?
Yeah, I think so.
Notice that in the first graph there that they're showing you, that's a growth. Because as you move to the right, it gets big, out of control pretty quick. And the other one's a decay. Because as you move to the right, values drop pretty hard. They're both asymptotic on the x-axis. Do you understand that?
Yes.
You're always going to get a positive y value. Either way. But when you're over here, for example, when x, if you have 2 to the x, just let me show you right quick. If you have 2 to the x, I'm going to have to, I don't want to move the computer. So anyway, if you have 2 to the x, and that's your function, then when we graph it, if x is -3, we get 1/8, right? Because that's 1 over 2 to the third. So when this is -3 back here, you get a little tiny value. If x is -10, you get a really tiny value, but it's still positive. So this thing is bounded below, but it never hits its floor. It's asymptotic on the x-axis. If it's -2, we get 1/4. If it's -1, we get 1/2. And if it's 1 or 0, we get a 1. And if x is 2, we get a 4. And you can start to see it get out of control because the next one's 8. So that's why it has the shape it has as it grows. This B value was greater than 1. And so we get a growth. Y'all follow?
Yep.
Cool. You see why if this were, well, let me show you this one. If I had y equals just the reverse of that, or the reciprocal, 1/2, where this is less than, I mean, between 0 and 1 to the x as I went to the right, then I would have 1/2 raised to the -3, which is the reciprocal of this to the 3. Are you familiar with that? Let me show you.
Yeah.
1/2 to the -3. I don't know where I'm going to go here. I'll erase this. 1/2 to the -3 is the same as this. This is one way to explain it. There's a couple ways to do it. It's 1 to the -3, which is 1, because 1 to the anything is 1. And this is 2 to the -3. So when I just told you this was 1, this is 1 over 2 to the -3, which is 2 to the 3rd. So when x is -3 in this situation, -3 back here, we're up here at 8, or it was 8 over here when it was +3. And then we get a 4 here, and we get a 2 here, and a 1 here, and then it starts falling down here like that, or decay, but it's still asymptotic on the x-axis, it's just been reversed. You think about transformations for just a minute. I could write this, instead of 1/2 to the x, I could write it as 2 to the -x. And when you affect the sign inside the functioning, before you function it, you put that sign there, that's a reflection over the y, which is what we have. Good? So it all fits together. All right. Now we're going to talk about more transformations. I think you guys will identify these really quick. We're using exponential ones, but the transformations remain the same. If you affect the x either by multiplying, by a negative or a positive, or by adding or subtracting, it's a horizontal move. If you affect the x before using it to function something. In our case, our x is in the exponent. So if you do something to x in the exponent, it's a horizontal something or other, the opposite of what you think, just like it's always been. If you do something to the front of the function, so you're using x on the function and then either multiplying or adding something beyond that, that's a vertical move. Exactly as you see. So, should be easy. Take a look at example 4. If the parent function we're talking about is 2 to the x, how is g different from that?
Oh, so it's
Right 1. Because it's affecting the exponent before we use it as an exponent, which means it's a horizontal move, the opposite of what you think. What about the next one?
function over the y.
Yep, we just discussed that one. And the next one? Vertical stretch of 3. Just like that. You guys agree. Please notice though in the vertical stretch, remember this one right here crossed at 1 because 2 to the 0 was 1. If you vertically stretch that by 3, then it's going to cross at 3. And that's where it's going to start. It's going to go like that. When you stretch it, it's going to affect the cross point on the y-axis. 3 times as big as 1. Okay? All right, just so you know. All right, now we are going to talk about the natural base E. How much of an explanation do you want for this? Or you want to just run with it? Okay, well, I will give you as much as I can without what you don't hear. There was this, I went to this, it's called the NCTM, it's called the National Council of Teachers of Mathematics. And I have, on occasion, gone to their week-long seminar, their week-long meetings that they have to help all kinds of math teachers become better math teachers. And one of the talks was called a high school explanation of E, or something like that. We all went, this is magic. We're all going to that. People were standing, they were sitting in the aisles, they were standing on the walls, everybody had a notebook, everybody was in there waiting for this guy. I left after about 45 minutes. The room was nearly empty after an hour and a half. It was ridiculous. It was not high school. But I will give you what you'll have to, it's a little bit fuzzy math. You'll have to take it on faith that I'm not going to try to run you in the ground with it. I didn't understand it. I understood quite a bit of what he said at the beginning. And then I went, this is not for my kids. And so I left. I will give you what I can without making you feel stupid or making you feel, but what that means is you're going to have to accept a bit of fuzziness. Here's the deal. Do you remember studying finance And they said, if you're going to compound something continuously, no, not continuously, not yet. If you were going to compound something, say, 4 times a year, every quarter, that the equation that we used was that the amount of money that you have is equal to the principal investment times 1 plus the interest rate, let's say 5% annually, divided by 4, that's how many times they're going to pay you, to the 4 times t. Now, let me explain all of this. We're going to do it again in the last section, but you've seen this before. What this 1 right here, by the way, this 1 hangs on to your principal for you and then causes it to grow like this. So if you get 5% annually, you're going to have to take that 5% and split it up into 4 equal pieces. Each of those pieces will be paid to you 4 times a year. So they're going to pay you 4 times as often as you would if it were annual. So this is how often they will pay you. This is the interest rate they will pay you at each of those quarters. So what I'm saying is that you have to divide here, cut your interest rate down here, but then you have 4 times as big an exponent here. And what I'm saying is that it's very slight. Don't get all excited about it. This will have a slightly larger effect on growing your money than this will on cutting it down. Because this is an exponent, this is division. Kind of order of operations kind of thing. But not by a lot. What I'm trying to get at is if you had your money compounded monthly, then this would be 12 and this would be 12. And so this is really small. This is the interest rate every month is small, but you're going to compound it 12 times as often. If you're going to compound daily, you get this, which is a super tiny number, but you're going to compound it a super lot of times. If you let the limit, you've seen limits before, as n, this is the n value here, as n goes to infinity. In other words, you're going to compound more and more and more and more often. Maybe we go from years, or from this, maybe we compound every hour. Maybe we compound every minute. Maybe every second. Maybe every picosecond. Maybe every 1/1,000,000th of a picosecond. You know what I'm saying? You compound every instant of time. That's when n is going to infinity. You have this inside here. I'm not worried about that. It's going to be 1 plus the interest rate, whatever it is, over pretty much over infinity, but a really large number raised to a really large exponent. If you do that, when we put a 1 here plus, I'm going to say I guess I'll leave it as a rate. You get the value of E, which is approximately 2.718. And that's why when we say it's going to compound continuously, that's why this thing, which is compounding periodically, turns into this. This is where the fuzzy math comes in. Because the R is here in this one, but it shows up here in the exponent on this one. This is compounding continuously, where your base, this thing right here is your base for the exponent, where your base, as n goes to infinity, becomes this. So you're going, how does that happen? I could show you more. I'm not going to. It's a waste of time. But I'm just saying it has to do with if you're going to invest and you're going to compound more often, you're really compounding continuously and the base turns into E. Very fuzzy, but that's all the explanation I'm giving you. So E is approximately 2.718. We will not use an approximation. I just want you to know about the size of it. Pi is 3.14. That's an approximation. E is 2.718. It's a good thing to have in your head. But we will use this button on your calculator. I'll get my calculator to show you, but I've got it. Okay. We will use, for those of you watching up here, you guys in the classroom, it's right here. Kitty corner to the number 4. It says e to the x as the blue thing. Okay, for you guys, I don't know if you can see this very well, but it's down here, right kitty corner to the 4. Do y'all find your e to the x?
Yes.
Calculator, you okay? Okay.
Yeah.
There is another e, which is above the divide sign. Do y'all see that? It's the same e. Don't use that one. Everything we do with e in here will be to raise it to something. So we will always use the e to the x key, not the e key. Don't do that. Okay? It's up there, but don't ever use it. not in these contexts. Okay. There is a bit more of an explanation for the theorem, and I'm not gonna go over this, but if you want more explanation about that theorem in the middle of page 251 that says exponential functions and the base e, shows you how to convert to a base that was just b to a base that is e. They give you a little bit more explanation. I'm not doing it. Okay. And you'll notice in the exploration, if you go to that, it might convince you more. It says choosing k so that e to the kx is the same as 2 to the x. There's a way to convert when your base changes from 2 to e and involves a k value, which you can find on the list. Okay, all right. Example 5 then is about that transforming I just discussed with you. We're not doing it. So moving on. Now we're going to talk about logistics. So you've gotten all your explanation of exponents that you're going to get for today. We're going to get a lot more before the chapter's over. Logistic curves. By the way, exponentials, if you're talking about something growing, exponential curves, if they're growing, grow without limit. There's nothing to limit it. Logistic ones, which is what we're going to discuss next, is usually about populations, in the long run and how they settle on a value if nothing happens to their little niche that they're in. If everything just stays the same, there will be as many births as there are deaths, and the population remains constant after a long time. Okay, so if we talk about, for example, bacteria in a petri dish, have you guys ever, have I discussed this with you before about growing bacteria in a petri dish with agar in the bottom? I have?
Yeah.
Yeah, we have, okay. Agar is a nutritional substance, and you take a swab and go swab the toilet and wipe it across that agar and then just set it aside in a nice environment with a good temperature, and it just eats that stuff. And eventually, some of the bacteria run through their lifespan and die, just like we do. Some of them, as the population grows, they starve to death because they can't get the food because others are better at it than they are. There's no predators, but there are predators in other things, other growing environments, right? That could kill you and eat, that could kill the young. You know, the wolf makes the caribou strong. Idea. You know what I'm saying? And Jack London. Woo. Okay. So what happens is we start out with a certain amount of bacteria. That would be, well, when I describe the actual logistic curve, it's going to be rather complex. Anyway, start out with a certain number that you swab in there. Nobody's going to count that, but maybe the agar changed by a certain portion of a milligram or something like that. But anyway, it gives you a start count for your bacteria. And then it's going to grow exponentially for a while because they're all young. They're all fed well. Nobody's competing. And we assume they're all fairly healthy to begin with. Okay, so it grows exponentially like that for a while. And then after a while, some things start to happen. Some things start to die off. Maybe the cell division isn't happening as efficiently anymore because they're not as healthy. Whatever. It starts to still grow. I mean, still growing, but it begins to level off until there are as many deaths as there are births. And then as they completely run out of agar, then they all die. But we're talking about to here. I don't know if I drew that very well. It's asymptotic at a particular value that's determined by the organism, food source, growing conditions, predatory situation, all that kind of stuff. This thing right here is little c. And it is called the carrying capacity. That's what I always call it. He calls it the limit to growth. You can understand the words for both of them, right? Okay. Here's why this is different with biologists than it is with us mathematicians. We did discuss this once, I think, when we were talking about functions. They always start with time equals 0. For us, we let it go beyond that. Because what happens when x is negative? And the answer is that piece of the exponential part is asymptotic on the x-axis. This is totally uninteresting to biologists because they're going to start the clock when they swab the petri dish. They don't care about what happened before, and then this has no meaning for them. It does for us because we got an asymptote on the bottom and a carrying capacity, horizontal line, carrying capacity, horizontal line on the top. So this thing is a fundamental function that we talked about, one of the 12, and it's always stuck between two. X-axis is one of them, and then the carrying capacity for the rest. So he shows you that logistic function at the top of page 253. And this is he's got two different ones. I need you to understand this, so when you're doing your exercises, you can default to the one that I'm gonna use. I have never known any biologist or anyone else studying population growth ever to use the first one. It's where it says definition logistic growth functions on the page just before the basic function thing. You see it? He says f of x equals c over 1 plus ab to the x. You see the ab to the x looks like what we just studied? We will never use that one. We will always use the continuous growth thing because this is a naturally occurring thing with populations. Naturally occurring things, you have a base of e. That's just always the rule. So one we will use exclusively is c over 1 plus ae to the negative kx. And in most cases, that's going to be negative kt for time. Okay. So let's go over to example 6. I guess I'll put the parent function up here so that you have something to compare. I'm not sure it's important that I write it down, but this is the one we will use exclusively in here. C, the carrying capacity is the numerator constant. That's kind of nice. So if you have to fit a logistic curve, you just got to go look at the numerator to figure out the carrying capacity if they ask you. Okay. And it's always 1 plus some A, and every book I've seen but this one, it's capital A, so that's what I'm going to make it, e to the negative kt. And the reason why I make it a capital A is so that you don't get hung up on the idea that perhaps this is the beginning amount. It is not. That is not the beginning amount. So if I put a little a there, you might assume that it has something to do with this and that these a's are the same because they're little and big. I mean, because they're little. They are not the same in these, and that's the reason why I make a distinction between the a's. Is that okay? That is not the beginning amount, so get over it. Example 6 says, graph the function, find the y-intercept, and the horizontal asymptotes. If you understood what I just said about this, you ought to be able to identify the horizontal asymptotes right now.
0.
Y equals 0, yes. And
C.
y equals 8. See the carrying capacity where it sits? In the A part of example 6? Are y'all got your eyes there? Okay. And it says find the y-intercept. That you can do arithmetically in your head too. The y-intercept will be when x is 0. It's always been that way. So if you want to find the y-intercept of something, let x be 0. If you let x be 0, what you end up with is 8 over 1 plus 3. 2. The arithmetic? Y'all see why that is the way it is? You okay? You refer to that for a minute. You understand what's going on? Yeah. Okay. In the B part then, what are the asymptotes? As equations?
Y equals 0, y equals 20.
Y'all agree? Yep. And what is the y-intercept for the beginning amount is what we're saying. What's the y-intercept, which is the beginning amount?
Is it 1? Wait, no, it's 3. No. Wait, oh, this is 20, I forgot.
It's 20 over 3. Weird number for a beginning amount, but that's, in this case, for the mathematics it's involved, it's 20 over 1 plus 2 e to the 0. And anything to the 0 is 1, so it's 20 over 1 plus 2 is 20 over 3. Y'all following? Yes.
What's the y-intercept on A?
Well, let x be 0. So you have 0.7 to the 0. That's 1. 3 times 1 is 1. 3 plus 1 is 4. 8 divided by 4 is 2. Catch all that? Good. You see how to read some of these things? Okay. Let's do a couple of examples for modeling so you know how to make your calculator work. And well, that'll be it. So one of these wants you to actually go to your stat editor and put in some values and fit a logistic curve and make a prediction, like we've done before. I'm not a logistic. I think this one's exponential. The next one's logistic. And the next one wants you to practice being able to put y equals and have a logistic function and use all your parentheses correctly and your division signs and all that kind of stuff. Okay, so now example 7 is a practical example about exponential. So now you got to backtrack and think where we were at the beginning. This is an exponential thing. It says, using the data in table 3.5 and assuming the growth is exponential, I'll tell you right there, when will the population of Austin surpass 1 million persons? Look at their table. There's only two values, but it's sufficient. We could fit a line through there perfectly. We could also fit a logistic. I'm sorry, no, an exponential through there perfectly. So here's what you do. Everybody do this with me. We're gonna go to the stat editor, hit edit, dump any lists that you have. So list 1 needs to be made up of. Can anybody tell me what you're gonna put in list 1?
0 and 5.
0 and 5. Remembering through the whole problem in your brain that 2010 is your 0 number. Okay? So 2010, I'm sorry, we're gonna put 0 and then a 5, and then we're gonna put those actual numbers, they're huge, in list 2 to go with them. Next thing we do after putting in data is go build a window. If you can't find it in the window, the rest of it doesn't make any sense. So now let's go to the window and think about what we're gonna put there. What would you like to put in for your x-min? 0? You could. I personally am going to put in -1 so that I can see my y-axis. That's not right on the edge of my screen. Has nothing to do with the problem. It's just so that I can push the y-axis over to the right of it. And I'm going to let it go out to.
What do you want to? What are we guessing where it's going to be?
What we want to know is what year will it be when they surpass 1 million?
Oh, so we don't know.
Yeah, so we don't know, but they're at 815,000 or 816,000 now. It's grown to 931. That's not too far off a million, so I let my x's go to 10. If I'm wrong, I'll squeeze it down. Okay, so I'm just as a roundabout number. Because in only 5 years, they've gone from 816 to 931. I don't think it's gonna take another 5 years. It'll probably happen in the whole 10 years. Anyway, that's what I'm thinking. And then, what do you like to be your y minimum?
800,000?
You could. I'd let it be more like 6 or 7, just so that you got a buffer zone, just so that your point's not sitting right on the bottom of your screen. So maybe let your y minimum be 700,000. Okay, what do you want to let your y max be? 1,200,000.
1 million.
1.2 million. That's fine. 1,200,000. That's what he wants it to be. Why 1,200,000 or why 1.2 million? Why?
Just because it's above 1 million, which is what we're looking for.
Yeah, we want to be able to see that horizontal line and have a little bit above it. You know what I'm saying? We want to predict at 1 million. We don't have 1 million in our table. We want to predict at 1 million, so I think we should go, I'd like you, a bit above so we can see that horizontal line. It's not right at the top of our screen. So that's just exactly what I chose, 1.2 million. And I scaled mine by 100,000, so I don't care, but just don't scale it by once because it'll just trying so hard. Okay, so that's a good window. Now go to y equals, clear out any values you have there and turn plot 1 on and hit graph. And it's not very dang exciting. 2 points. But we can see them, which means we designed our window pretty well. Okay. Now we go to stat, over to calc, and we're doing what kind of regression? Exponential, because that's what they told us in the problem. We're not doing logistic, it's exponential. So go down there, it's the 0 one. EXP reg, hit enter, and fill in the details. Mine has a different operating system than it does, so it's going to work for me. Oops. Everybody get it done and hit enter, and it's now in Y1. Did you store it in Y1? Yep. Okay. Perfect fit, as it should be. It's only 2 points. Hit the graph, and the graph isn't very exciting either. What do we do next? Back to y equals. We'll put in what? Y2 equals 1 million. And hit graph, we'll have a red line, and it does cut it in the window that we decided on. Go find it. 7.659.
Yep.
And of course, the y value is 1 million because we're on that horizontal line where it intersects.
So
Now, interpret the problem. Interpret what we've done all this way through. How do you interpret the values?
So that's 7.6 years after 2010. So.
And I would accept 2017. He claims it's 2018.
All right.
But it's interesting why he does. And perhaps you should consider this if you do a problem like this. He says in the interpret portion of the example set, you see down where it says interpret? See it? Example 7, the words interpret. He says, because 7.66 years after the middle of 2010. That's how he perceives these times. Not the beginning of 2010, but each of our years is the middle of it, in July. So he's saying if we perceive each of these years as being the middle of the year, then 7.66 years later is early in 2018.
Oh, yeah, it says years after July 1st.
That's the way we have to consider July 1st, that's in the middle of the year. So 7.66 is, the 6.6 is more than half a year turn into 2018 in January somewhere. See what I'm saying? That's why he interpreted 2018. If you gave me 2017, I'd be fine. You had to do the problem right to get that close. So I'm good with it. Interpretation is ticklish sometimes, so just try to read very carefully. Last example wants to know if you're good enough at putting things in your calculator, good enough and comfortable enough with it to actually graph an equation that they give you and use it to make a prediction. So we're not going to plot points and make it fit one. We're going to take the equation they give us and see if we can put it in correctly. So go to y equals, and this is a logistic one, but it's already written logistically. You don't have to interpret it that way. It says P of t, the population as a function of time, is equal to that monstrously huge number up there, which we interpret as the carrying capacity, now that's logistic, over that massive, ugly, nasty denominator. Do your best. Do you think we need to make adjustments to our window based on what you're seeing and let me know?
Yes.
Yep.
I'm going to have mine go up to about 1.8 million because the carrying capacity is 1.5 million, right? So I'm going to change my window up a little bit. Go to 1.8. I don't know what the beginning is. That 5402, that's not your beginning amount, so get over it. I don't want to discuss it with graph.
So how would we use that formula to describe our window? Like what are we like looking at?
Well, notice that the carrying capacity is 1.5 million. So we want to be able to see that thing approach 1.5 million. So I bumped mine up to 1.8 for the Y maximum so that I can see that line of approach. Question is, how many years? Based on a longitudinal census, a logistic model for the population of San Diego after 1900. So our X values are going to have to be pretty good size because we're talking 1900 up to the present. So I'm thinking that our X values maybe better go from -10 instead, so we can see the Y-axis up to maybe 120. You thinking? You know what I'm saying?
Yeah.
Okay, because we got to go a full century through. And I'm still not seeing a graph. Oh, here it comes, here it comes, here it comes. This is what I got leaving the Y minimum at 700,000. So I'm seeing something, but boy, I want to adjust my window. I want to be able to see the whole thing.
Yeah.
So I'm going to go back to window and change my Y minimum to be about maybe negative.
I put negative 10,000, just so I could see below.
Yeah, I did 15,000, so yeah, right. And you can see most of it, and you can see it starting to turn after the first 120, right?
Yep.
Now graph the line Y equals 1 million, because that's our prediction for this one too. So Y2 equals 1 million. Let's see if we should be able to see that line, see if it hits a curve. It does, quite clearly.
Yep.
So we go calculate and intersect. We'll find it, it intersects at. What do you like to interpret that? Talking about San Diego. This is how you qualify it to cover your rear end, just in case this equation isn't accurate. You would say, according to the equation they gave us, San Diego should reach 1 million people in 1985. Okay, y'all see how that happened?
Yep.
The main purpose for this one was to see if you could enter one of those ugly, nasty logistics, and it was pretty easy because you have a fraction key in your calculator, right? Did y'all use a fraction key? When we didn't have that before in those old calculators, boy, you had to be careful with the parentheses and everything. But now, yeah, that fraction key is not too bad at all. Especially when the cursor stays in the exponent until you move it off. You don't have to worry about that either. That's nice. Okay, and there we are at the exercises.
We need our assignment paper.
Oh,
Guys,
guys,
I copied it. Made a huge effort to go upstairs and copy it. Okay, ladies, I will email you both on your Sugar Salem account a copy of the chapter assignment list about as soon as I stop this recording, okay?
Thank you.
All right. Let's see, how do I stop the recording? Oh, right there.